Sample exam 4. Question number 1. A population consists of 20% zeros, 40% ones, and 40% twos. A random sample of x1 and x2 of size 2 is selected with replacement. What is the probability that the absolute value of x2 minus x1 is equal to 1? So exam 4, problem number 1, we're asked to find the probability that the absolute value of this difference is 1. And so we just go through each, all the possible scenarios. x1 could be 0 and x2 1, 1 0, 1 2, and 2 1. And then since they're independent random samples, we can just take the probability of each event. So there's 20% zeros. So the probability of picking a 0 is 20%. 0.4, and you can do that across, and it adds to 0.48. Problem number 2. Let xy have the joint density function f of xy, which is equal to 6 times 1 minus x minus y, xy between 0 and 1, and x plus y between 0 and 1. What is the probability that x is between 0 and 1/2? Now problem number 2, we're asked to find the probability that x is between 0 and 1/2. Here is our region, or our domain, and we want to integrate this for x less than 1/2. And so one way to think about this, we're given the joint density, and so we need the marginal density. So if we integrate out y first, that's going from 0 to 1 minus x. And then we integrate x from 1/2 to 0, or 0 to 1/2. And that's what we do here. So this first piece is the part that's integrating out y to get to the marginal distribution of x. So we integrate this, and we'll dy first. So we'll treat this whole piece as a constant. That's what we do here. So it's y times that, and then here it's y squared over 2, which changes that to a 3. Plug in the values. Combine those terms, we get this. Integrate that from 0 to 1/2. Plug in the values. Boom. Answer 7/8. Problem number 3. A point xy is chosen at random from the unit disk x squared plus y squared less than or equal to 1, according to a uniform distribution on that disk. If the conditional density function of x given y equal to little y is f of xy, what is the value of f of 0.25 given 0.75? So number 3, we're given a uniform density over a region of this circle. Well, the area of that circle is pi, so the area has to integrate to 1, or the density, and so the joint distribution has to be 1 over pi. Okay, and we're asked to find the conditional of x given y. So we need the density of y, so we integrate out x. And x goes from this boundary to that boundary, which are these. Integrate that out, plug in the boundaries, you get this. So then f of x given y is in the joint density divided by the marginal, and you get this. And then to find f of 0.2 and given 0.7, you just plug in the values. And then that simplifies to one of the answers, 2 over square root of 7. Problem number 4. A random sample from 1 to n of size n is selected from a normal population with mean mu and standard deviation 1. Later, an additional independent observation, x n plus 1, is obtained from the same population. What is the distribution of x of n plus 1 minus mu squared plus the sum from 1 to n of xi minus x bar quantity squared, where x bar is the sample mean of the first n observations? Number 4, we are asked to find what's the distribution of this quantity here. So one note is that this sum divided by its variance, but the variance is 1, so it's like dividing by 1, so you just get this quantity. It's chi-squared within minus 1. And so that's a pretty critical part, is you have to divide by the variance. But it's 1, so we don't have to. So then this quantity is, since x is a normal and has a mean mu and a variance 1, so when we take that value minus the mean divided by the standard deviation, that's a standard normal. So when you square it, you get a chi-squared 1. And so this is chi-squared 1 and this is chi-squared n, and so when you add chi-squared, you add the degrees of freedom, so the answer is chi-squared n. Number 5. A family has 5 children. Assuming that the probability of a girl on each birth was 1/2 and that the 5 births are independent, what's the probability that the family has at least one girl given that they have at least one boy? So number 5, we're given that we let x be the number of girls, and x would be a binomial with n equal 5 and the parameter 1/2. And we're asked to find the probability that we're greater than or equal to 1 given that x is less than or equal to 4. So we have at least one boy. So the conditional can be written as the joint over the marginal, and then it's easier to take the 1 minus. This is 1 minus x equals 0 and 0.5, and then this is 1 minus x is 5, so 0 and 5. And then we just plug in the values into the binomial, solve it, we get 30 over 31. Number 6, let t equal to this quantity, k times x plus y, divided by the square root of z squared plus w squared, where x, y, z, w are independent normal random variables with mean 0 and variance sigma squared, which is positive. For exactly one value of k, t, capital T has a t distribution. If r denotes the degrees of freedom of that distribution, then the pair k and r is equal to. So number 6, we know we're given that x, y, z, and w are all independent random normals with mean 0 and variance sigma squared. So if a linear combinations of normal variables is normal, so x plus y would be normal 0 with the variance 2 sigma squared. So then if we take this sum and divide by the standard deviation, we get a standard normal. Now z minus 0, which is the mean, divided by standard deviation is standard normal. So we square it, we get a chi-squared. Same way for w over sigma squared is chi-squared. And then if we were to add these two pieces together, which is this, we get a chi-squared 2. So we're going to take a standard normal divided by the square root of a chi-squared divided by the degrees of freedom, and that's a t distribution, and that's what we do here. Now this sigma radical 2 cancels with this, radical 2 sigma squared, simplifies to this. So the problem gives us k times this, but we just want this because this is chi-squared 2. So k is 1 and the degrees of freedom is 2. Number 7, suppose the straight line of the form y equals bx plus 1 is fitted to 4 data points, 0, 2, 1, 2, 2, 0, 3, negative 1, by the method of least squares. What is b? So in number 7, we want to find a least squares estimate of b. So we take the sum of squared errors, we take the partial or derivative with respect to b of this, so we get 2 times this middle, then the 2 minus 1, and then times using the chain rule, the derivative of that. We set it equal to 0. We solve for beta, and we get this. And then we're also given the data point, so we can find the sum of xi, yi. That's minus 1. Sum of x is minus 6. Sum of I squared is 14. So the answer is b is equal to minus 1/2. Number 8. Let x1, x2, and x3 be a random sample from a distribution with density function f of x, which is equal to 2x, where x is between 0 and 1. Let y1, y2, and y3 be the order statistics. What is the expected value of y3? So number 8, we're asked to find the expected value of y3, which is the largest order statistic. We're given that the density is 2x, and we can find the CDF of this by integrating from 0 to x, and we get x squared. So then the density of the largest order statistic is going to be n3 times the CDF squared, which that times the density. So we get this. So then we want to just take the expected value of this function from 0 to 1, integrate, we get 6, 7 times x to the 7th, plug in the values, we get 6/7 is the answer. Number 9, suppose x and y are independent random variables, each with density function f of x, which is 2x times theta squared, for x between 0 and 1/theta. If c times x plus 2y is an unbiased estimator of 1/theta, then c is equal to number 9. We're asked to find the constant c that makes it a unbiased estimate of 1/theta. So let's find we're given the density. Let's find what the expected value of this is. So we plug in an x, and that's why we get the x squared here, because it's x 2x theta squared. So I just brought it in. We're integrating with respect to x, so this is going to be 2/3 x cubed times theta squared. Plug in our limits, and we get 2/3 times 1/theta. So here's the expression we're asked to find the expected value for. And so we can take in the expected value, c times x, plus 2 times c times the expected value of y. And these are constants. That's why they can be brought out of the expectation. And x and y are independent, and they both have the same density. So the expected value of x is 2/3 1/theta, and then that c is out front. And then this has the same expectation, so we bring it in. Simplify it a little bit. Simplify it a little more. And we want this equal to 1/theta. So the only way, that way it's unbiased. The only way for that to happen is that this piece equal to 1, 2c equal to 1, or c equal to 1/2. And that's our answer.